Today I get to tell you about one of my very favorite things in this course. It's a Fourier series. It's a mathematical thing, and if, you get bogged down in the math, it can get kind of dull, but then you realize all the amazing things you can do with it, and it's really exciting. So we're going to start with the math. Try not to get bogged down, pay attention, and then after we get to the math, I'm going to show you cool things you can do with a Fourier series. Alright, so a Fourier series is a way to transform from looking at our information in one way into looking at it another way, looking at a function in a different way. Alright? And because a Fourier series is a transformation, sometimes I may slip and call it a Fourier transform. It turns out a Fourier transform is technically something slightly different. I'll tell you what it is a little later in today's presentation. Technically, what we do in this class is a Fourier series. But let's talk about other types of transformations. In particular, I want to talk about a Taylor series because I believe most of you have seen a Taylor series. And the basic idea with a Taylor series is that if I have some function f of x, which is defined on some interval for x, I can write that function as a polynomial, as a constant, plus a constant times x, plus a constant times x squared, plus a constant times x cubed, and so forth. All right? So the basic idea here is I can write a function as a sum of other functions, right? But when I do that, I can kind of imagine this. I have a way, I have something I can use to find what these constants are in my equation, right? If I know a, that constant a is a function of n, I can use that to reconstruct this function f of x. So the function a is a function of n is in a sense equivalent to the function f of x. But it's looking at the function in a very different way, sometimes a more useful way. And then the inverse transform is just adding all of these polynomials together and getting our original function back. Right? A Fourier series is kind of like a Taylor series. It's just I have a function and I'm writing it as a sum of other functions. So Fourier, what his theorem was, is he said any periodic function can be written as a sum of sines and cosines. So for example, if I have a function f of time, which is periodic in time with a period capital T, then I can write that function as this function of sines and cosines, this sum of sines and cosines, where omega naught is 2 pi over the period. So it's not just any sines in the world, it's these specific sines and cosines with particular frequencies. By the way, this is not only valid just for time. I can also write a Fourier series for position. For example, I can, instead of writing a function of time, I can write it as a function of x, but in that case the period just goes to the fundamental wavelength, and omega naught gets replaced with k naught, and so forth. So you just find the equivalent for x. If anything I have in time, I find the equivalent for that in x, and I can write a Fourier series in x. I can write a Fourier series for something that's periodic in anything, something that's periodic in salinity, something that's periodic in intensity, something that's periodic in happiness, something that's periodic in dankness. I can write that function as a sum of sines and cosines using a Fourier series. Your book showed an example where I took sine waves and added them together to make a square wave. So the point is I can add a bunch of sine waves together and get something which is not at all like a sine wave. All right? And any periodic function, whatever it looks like, we can write that as a sum of sine waves. But how do I find how much, right? Basically, doing a Fourier series is finding these constants to put in here, right? So I know what the period of my function is, how long I have to wait for it to repeat. So I can find omega naught, and that determines which frequencies are in my sum. In order to write my Fourier series, then, I just need to know what these amplitudes are, a sub n and b sub n. How do I find them? So doing a Fourier series is the process of finding a sub m and b sub m. So how do I find them? Well, it turns out we can come up with some general formulas that tell us for whatever periodic function you want, this is how you find a sub n and this is how you find b sub m. And deriving them is actually not that hard. What we do is we use something called orthogonality that you'll learn about in another physics class. But the point is, the whole point behind it is, some functions, if you multiply them together and integrate over the right thing, you can make them go to 0. All right? Let me just show you how this works. So what I'm going to do is I'm going to take this equation and I'm going to multiply both sides by a sine wave. It's going to be one of the sine waves in my sum. So let's say sine of n omega naught t. I'm going to multiply this by that, right? Now, m takes on all values from 0 to infinity. So if n was like 4, right, that's one of these sine waves in the sum, but only one of them, right? But I'm not going to tell you what n is. I'm not going to say it's 4 or 7. Let's just call it n for right now. It's one of the sine waves in the sum, all right? If I multiply both sides, then over here I'm going to get the sum from m equals 0 to infinity of a sub m sine m omega naught t, and then I'm multiplying by sine n omega naught t, right? And then I have to multiply the cosine by that as well. So b sub m cosine n omega naught t times sine of n omega naught t. So I just multiplied both sides by sine of omega naught t. The next thing I'm going to do is I'm going to integrate both sides with respect to time over one period. I'll start at some time tau and go to tau plus 1 period later. I'm going to do the same thing over here. So I'll take this whole sum here and I'm going to integrate with respect to time from time tau to tau plus t, right? So I've done the same thing to both sides. All right, so I've got this integral over here, and if I know what my function is I'm trying to write as a Fourier series, hopefully I can do this integral. Let's look at the other side over here, all right? So I've got the integral of a sum, right? If I have the integral of a bunch of things added together, I can integrate each thing added together separately, right? I can exchange the order of integration and summation. So this is really just a sum of a whole bunch of terms. Some of them are a constant times a sine, and some of them are a constant times a cosine times a sine, all right? But let's look at what these sines and cosines we're looking at look like, all right? So if I take, for example, this is my n equals 1 and my n equals 2, right? So if I multiply sine of omega t times sine of, or m, however you want to think about it, sine of omega naught t times sine of 2 omega naught t, all right? Sine of omega naught t is the blue curve, sine of 2 omega naught t is the purple curve, all right? When we notice that the purple curve kind of repeats itself about the middle, but the blue curve is inverse of itself about the middle. So when I multiply them together, this side and this side will have opposite signs. When I multiply them together, I get this curve right here. And what you see is, when I integrate from here to here, I get the negative of what I integrate from here to here. So if I integrate over an entire period, this is going to integrate to 0. All right, so that's 1 omega naught t sine of 2 omega naught t. What about sine of 1 omega naught t times sine of 3 omega naught t? Once again, here's omega naught t, here's 3 omega naught t. We multiply them together, and once again we get something that when I integrate from here to here, I get 0, right? It's positive for part of it, but it's negative for part of it. And what happens is I end up integrating, and anytime I multiply two different sine waves together and integrate over, you know, a full period, it turns out that this is going to integrate to 0. Sine of 2 omega naught t, sine of 5 omega naught t. Once again, I multiply them together and I get something that averages to 0. So when I integrate over a full number of periods, an integer number of periods, it integrates to 0. If I take a cosine and a sine and I multiply them together, once again I get something which, by multiplying together, I get a function which integrates to 0 if I integrate over one period. All right? But the only exception is when I multiply a sine by itself, the same sign by itself, then it's always positive, and I never get an integral that goes to 0. All right? So basically the point was, I had this whole sum up here. If I go back up here, I have this whole sum. All of these things I'm integrating, when I integrate over a full period, they are going to integrate to 0, except for the one where for the sine where m is equal to n. So all the sines times cosines, all right, and integrate those. One quick way to think about that is if I integrate symmetrically about the origin, right? Cosine is even, sine is odd. If I multiply a sine times a cosine, that's odd. I integrate over an odd interval, that'll go to 0, all right? But anytime I multiply my cosine times my sine and I integrate over a full period, for every value of m and m, n and m, those go to 0. The sines all integrate to 0 unless n equals m, and so what I'm left with is just one term for my sum, the m equals n term. So this is just going to be a sub n, the integral over one period of, let's see, the a sub n came out of my integral. I put it out there because it was a constant, right? And then they were just left with sine squared of n omega naught t dt, all right? And of course the integral is the area under a curve. And if we look at the sine wave again, let's zip ahead here. There we go. If you take a sine wave and square it, what you get is a sine wave that oscillates at twice the frequency, but it's been shifted up so it oscillates about a half. All right? So it goes from 0 to 1 instead of -1 to 1. All right? Now, an integral is just the area under the curve, and the area under a curve is just the average height of the curve times the length. The average height of sine squared, then, if I integrate over an entire integer number of periods, is 1/2. So I can come up to my equation, and I'm going to say, here we are. This integral is just the area under the curve, and the area under the curve is just how far we integrate, which is 1 period, times the average of the integrand, which was 1/2. All right, so there we have it. This integral right here is equal to an t to the 1/2, which means I can write a sub n is just going to equal, I solved this, right? It's just going to be 2 over the period, the integral over 1 period of my function times sine n omega naught t dt. All right, this is not equal to that. This is a separate thing I wrote, right? Okay, and I've written that in a table in your book. Here's the table reproduced right here. All right, so our Fourier series is just this, all right, that this is the one we found. We said for a sub m, we just integrate over 1 period, because remember 2 pi over omega naught is the fundamental period that our repeating function repeats at, all right? And we had in front, we had 2 over the period, but that's the same thing as omega naught over pi, right? So this is the equation we just got, all right, right there. If you do cosine, you get the same thing, except you have a cosine in there, all right? There's an exception, though, when m is equal to 0, right? A sub 0, it doesn't matter what it is, because that's the thing we multiply by sine of 0 in our sum. And sine of 0 is always 0, so it doesn't matter what that is, right? We don't even worry about what a sub 0 is. B sub 0 is a little special because, remember, we multiply by a cosine or a sine, in this case a cosine, and we integrate both sides. For b sub 0, we're multiplying by cosine of 0 times omega naught t, all right? And that's just 0. Cosine of 0 is 1. So I said that the average value of cosine squared or sine squared was 1/2. There's one exception. Cosine of 0, its average value is 1 because it's always 1, right? So there's a factor of 2 difference between this integral and this integral. And where's the cosine in this integral over here? This one has the cosine. Well, it's cosine of 0, right? Where m is equal to 0, so that's just 1. Anyway, so that's where these integrals come from. If you use these integrals, you can find your a sub m's, and your b sub m's, or your a sub n's, b sub n's, right? It's just an index, call it m or n, however you like. And then you can add them together to get your original function back, all right? Now, we did the example of square wave. Writing a square wave is a sum of sines and cosines, all right? So I've got a square wave. It's got some period, right? I go from here to here, and it repeats, all right? It's got some height, h, right? Call that h, all right? And it just goes up to h for a while, for half a period. So it goes up to h for half a period, then it goes down to 0 for half a period. Up to h for half a period, down to 0 for half a period, all right? I want to write that as a sums of sines and cosines, all right? So that means I need to find my a sub n's and my b sub n's. So if I look right here, here's my a sub n's and my b sub n's, right? For the a sub n's, we're going to multiply this by a sine wave and integrate, all right? But I'm not actually going to do that integral. I'm going to show you a shortcut, all right? Sine is an odd function. If I plot a sine wave, it looks like this, right? Right? And if I go to plus x, or if I go to minus x, it swaps the sign of the sine, right? So sine of minus x is equal to minus sine of x, right? If I have a function, and if I evaluate it at minus x and it's equal to minus itself at x, that is what we call an odd function. So if we go positive x and minus or negative x and compare the values we get, one is just minus 1 times the other. That's an odd function. Cosine is an even function, right? Cosine starts up here and goes down, right? Cosine is an even, which means f of minus x is just equal to f of x, all right? So sine is odd, cosine is even, all right? It turns out that the square wave, now I could have made a square wave that started at 0 and went up or whatever, but the way I've drawn it, it's symmetric about the origin. So the square wave that I have given you here, it's an even function. Even functions are made up of even functions, all right? So it turns out there will be, just looking at this and knowing it's an even function, I know that there will be no sines. So I know that all of my a sub m's are 0. If I doubted that, I could go ahead and calculate it, right? I could say a sub m is equal to 2 over t integral from tau to tau plus t f of t sine omega m omega naught t dt, right? That's the function I integrate to find a sub m, and you will find that it is going to be 0, all right, for every value of m. But once again, just looking at that, and one way to think about this is I can start my integral, even though in a formula it says you start from 0 and integrate to 1 period, 2 pi over omega naught, once again is a period. Really, because it's periodic, it doesn't matter where I start my integral as long as I integrate over 1 period. So instead of integrating from 0 to 1 period, what if I integrate from minus half a period to half a period, all right? My square wave is an even function. My sines are odd. If I multiply them together, I get an odd function. And if I integrate an odd function from some minus value to some plus value symmetrically about the origin, that's going to integrate to 0, right? It's going to be negative as much as it's positive. So you can go through, you can plug this in and convince it to yourself, or you can use some hand-waving arguments and you realize anytime I have an even function, there's going to be no sine wave in it, right? All my sines will be 0. Also, if I had an odd function, anytime I have an odd function, I do a Fourier series, I know all the cosines are going to be 0, all right? But I know all of my a sub m's are equal to 0. So now I just need to find the b sub m's. All right, for my b sub m's, my formula is 2 over the period, integral from tau to tau plus 1 period. My function times cosine of m omega naught t dt. So I just have to evaluate this function here in order to evaluate this integral to find out what b sub m is and find out how much of all the cosines I need to add together to make my square wave. All right? Now, a few things to note. Once again, this doesn't look exactly the same as on the formula sheet up here, but that's because I have noted that the period is equal to 2 pi over omega naught and vice versa, all right? So it was easier to write with the period, so I wrote it that way, okay? Now, I just need to do this integral, right? What is the function? What function do I plug into my integral that's a square wave? Well, what I'm going to do is I'm going to say, look, I don't have an analytic function for my square wave, but I'm going to break my integral up into parts. So let's integrate from minus half a period to half a period, from here to here, all right? From here to here, my function is 0. From here to here, my function is 0. So I integrate from here to here, I get 0. I integrate from here to here, I get 0. And then I integrate from here to here. So basically, I'm going to break my integral up. I'm going to integrate from minus t over 2 to t over 2, right? So I'm starting at minus t over 2, f of t cosine m omega naught t dt. So I'm going to integrate symmetrically about the origin, just because it's going to make my integral easier to do. And then what I'm going to do is I'm going to break this up into pieces, because I don't have an analytic version of f of t, but I know what f of t is for certain regions, right? So f of t from negative t over 2 to negative t over 4, this is equal to 0. From negative t over 4 to t over 4, this is equal to, right, that's when we go from here to here, that's when it's at its full height, it's equal to h. And then from t over 4 to t over 2, it's equal to 0 again. So I'm going to break this integral up into 3 parts. I'm going to have the integral from negative t over 2 to t over negative t over 4, and then I'm going to have an integral from negative t over 4 to positive t over 4, and then I'm going to have the integral from t over 4 to t over 2, right? And in each one of them, I'm putting all this stuff in here, cosine, blah, blah, right? So I put all of this stuff in. So I'm basically, right, I'm finding the area under the curve, but I'm breaking it up into pieces. And I'm allowed to do that, right? Just break my integral up into pieces. And then what I'm going to do is I'm going to come along and I'm going to say, look, from negative t over 2 to negative t over 4, that's when my function is equal to 0. So this is going to go to 0. All right? From t over 4 to t over 2, it's also equal to 0. So that function's going to go away. So I broke my integral up into pieces. Over those pieces, I knew how to write my function. All right? Okay, so those go to 0. I'm just left with this one. So now I'm left with b sub m is equal to t2 over t, the integral from negative t over 4 to t over 4. F of x is h in that region, right? So in this region, f of x is just h. All right? And then I've just got cosine of m omega naught t dt. All right? Can I do that integral? Yeah, the h comes out, so it's 2h over t. When I integrate cosine, I'm just going to get, you know, it's the inverse derivative, right? So instead of bringing out an m and omega naught, I bring out a 1 over m omega naught. And then the derivative of sine is cosine, so the integral of cosine is sine. So this is just sine m omega naught t, evaluated between negative t over 4 and t over 4. All right? And that's just going to be, well, first of all, let's look at this right here. So I said that omega naught is equal to 2 pi over t, so let's plug that in. So we've got 2h over t, 1 over m, and then omega naught is 2 pi over t. All right, so my 2's cancel and my t's cancel. That's glorious. And then I evaluate my sine here. I've got sine at m omega naught t over 4, and minus sine m omega naught negative t over 4. Remember, sine's an odd function. So I can bring this minus sign out and cancel that one. And then I'm just left with h over m pi here. And then I've got two of these sines, so it's going to be 2 sine of m omega naught t over 4. Okay, but I can do better than that, because omega naught, remember, is 2 pi over t, so this is 2 pi over t times t over 4. And then what I'm left with, right, the t's cancel out, and I've got 2 pi over 4, that's pi over 2. So I'm left with b sub m was equal to 2h over m pi, right, 2h over m pi, then sine of m pi over 4. And I look at this and I say, okay, did I do that? Yes. Okay. Now, oh, sorry, I had a 2 pi over 4, so it's m pi over 2. Good. I was getting a little worried here. I wasn't getting what I expected. Okay, so if I take sine of m pi over 2, what is that going to be equal to? If m is equal to 1, all right, remember, we don't care about m equals, let's see. We're going to deal with m equals 0 later, right? M equals 0 is a special case with a different integral. So let's stick with m equals 1, m equals 2, 3, 4, 5, 6, 7, and so forth. What is sine of m pi over 2 for each value of m? If m is equal to 1, that's just sine of pi over 2. That's 1. If m is equal to 2, that's sine of pi, which is 0. If m is equal to 3, sine of 3 pi halves, that's negative 1. For 4, we get 0. For 5, we get 1. For 6, we get 0. For 7, we get minus 1. So basically what happens is b sub m is 0 for every even value of m. And for odd values, it alternates between 1 and minus 1. All right? So I can write this as b sub m equals 0 for even m, and b sub m is equal to negative 1 to the something for odd m. So negative 1 to some power. So let's say, like, if I put 2m right here, if I plug in m equals 1, that's negative 1 squared. If I put in, no, that's not what I want. I want m plus 1 divided by 2. Let's think about that. If I plug in m equals 1, 1 plus 1 is 2. Divide by 2, that's m to the first power. All right? And that gives me minus 1. If I plug in m equals 3, that's 4 divided by 2, that's 2, right? And that gives me negative 1 squared, which is plus 1. So it looks like I have something that alternates as I go from odd m's, but I'm off by a power of m, so I better add another 1 into there. But that's the basic idea. I get an alternating series of minus 1s as I go across my odd m's, and all of my even m's, b sub m is equal to 0, if that makes sense. Sorry that was a little confusing there. All right? What about, we have one thing we still need to think about, though, and that's b sub 0, right? B sub 0 was a different integral, right? There was a factor of 2 missing, and it's just the integral of f of t dt, right? Because cosine of 0, 0 from tau to tau plus 1 period. All right? But remember, b sub 0, you can always remember, b sub 0 is just the average of my function, right? I just take the area under the curve divided by how far I integrate it. That's just the average height of my function. And if I look at my square wave, right, the average height is just h over 2, just half of h. So that's just going to be h over 2. All right? H over 2. So I found all of my b sub m's, I can plug them in, right? So basically I got h over 2, I'm going to let h equal 1. Then over here we have 2 times negative 1 to the n minus 1 over 2, right? I had n plus 1, but I had to add an extra 1. I could have also subtracted a 1, that would do it too. And then I get m minus 1 over 2, all right? Over n pi. And then I multiply my cosine it. So this is my b sub n right here. This is my b sub 0 right here. That's what I found. I plug them in and I get this function. If I only sum up to 1, I get a sine wave. If I sum up to 3, right, I only get the odd one, so now I'm adding 2 sine waves together. If I sum up to 5, it looks like this. If I sum up to 7, it looks like this. 9 looks like this. If I sum up to 101, it's starting to look like a real square wave. So the point was, I was able to find these coefficients, then I can plug them into my sum and write my square wave as a sum of cosines, right, as a sum of sine waves. All right? So that's the basic idea. Taking a Fourier series is basically finding the coefficients that I put in my sum so I can write my function as a sum of sines and cosines. Now you know how to do it. What's it good for? Well, it turns out Fourier series and Fourier transforms are good for an awful lot of things, like signal analysis. Imagine you're down in the lab and there's some noise. You do a Fourier transform, it shows you how much there are of different sine waves in your series. Maybe you see a big spike at 60 hertz and you say, oh, there must be noise from, you know, the wall voltage oscillating at 60 hertz. That's where my noise is coming from. So you can analyze signals that way. When you take a class on differential equations, you will find that Fourier series and Fourier transforms are a very useful way to solve a whole class of differential equations. Crystallography. You shine light at a crystal and it scatters the light. It turns out that the pattern it makes is a Fourier transform, and by inverting the Fourier transform, you can figure out what crystal it was that scattered the light. You can figure out how the atoms were arranged in that crystal. Shor's algorithm. If you've ever heard of Shor's algorithm, that is a cool technique where you can use quantum computation to crack encryption. So if you can figure out how to make a quantum computer that works well enough, you can, you know, break into bank accounts, figure out what governments are saying and whatnot, right? Well, it turns out that Shor's algorithm, the quantum algorithm that lets you crack these codes, is based on Fourier series and Fourier transforms. There's cool image processing you can do. Like you can remove dust and aging from pictures. You can find features. You can, you know, help find shapes. You know, you're trying to do image recognition. Fourier transforms are used heavily in image processing. Sound processing. You want to remove hiss or some noise or some popping from some music. The Fourier series will help you do that. There's a thing called Fourier transform spectroscopy, where you take light coming from something and you take the Fourier transform of the signal you get, and you can figure out what frequencies were in that, where it was in that light, and then you can determine what molecules were making that light. So you can figure out, you know, you can have a flame, you can figure out what's burning in the flame. All right, I could just go on and on. Fourier series are used for just tons of really good things. The one we're going to actually do as an example in this class, the one that's covered in your book, are waves on a finite string. So imagine I have a guitar string, and I pluck it, and the string does some crazy stuff. How can I understand the crazy stuff it does? How can I understand the sound that it makes? Well, we know whatever crazy stuff is going on my guitar string, I can think of it as a sum of the harmonic modes on the string. So if I could take the initial state of my string and write it as a sum of these harmonic modes, I know how the harmonic modes oscillate, so I could tell you how the string oscillates from then on. All I have to do is take the initial state of my string, write it as a sum of these harmonics, and I can tell you what it does at all times afterwards. And I can tell you how much of different frequencies are oscillating in my string. All right? So I want to write a function, the shape of my string, as a sum of these harmonics. Well, these harmonics are sine waves, right? So maybe I can use a Fourier series. Well, the problem is a Fourier series applies to a periodic function. My guitar string is not a periodic function. It's only defined from 0 to L, right? Periodic functions have to repeat forever and ever. But what I can do is I can say, look, imagine I stretch my guitar string to some shape. I can imagine that shape as part of an infinite periodic function. So even though I only care about what that function does on the length of my guitar string, I can imagine that it's an infinite periodic function. So what infinite periodic function do I want? Do I want to just take the shape of my guitar string and repeat it over and over again? Well, what I want is this. When I do my Fourier series, I want the terms that show up in my Fourier series to be precisely these harmonics. These harmonics are sine waves. They're not cosines. I don't have a harmonic where the string is up at the end, right? I have all of my harmonics where the strings are fixed at the end. So at x equals 0, my string goes to 0. I only want sine waves. If I only want sine waves, that means I better imagine this periodic function that my guitar string is part of, right? I'm going to imagine that my guitar string is just part of this infinite periodic function. This infinite periodic function needs to be odd so that I will only get sine waves. All right? So I can imagine this. Imagine I take my guitar string and I reflect it. I make an odd function out of it, and then I repeat that over and over again. All right? So that only has sines. The next question is, does it have the correct sines? Remember, my guitar string, the fundamental wavelength, the wavelength of the fundamental is 2L. So I want my fundamental, the lowest frequency, the lowest spatial frequency, the lowest wave number wave in my Fourier series to repeat every 2L, not every L. All right? Well, if I do this, mirror the guitar string about the origin and then repeat that over and over again, I get something that repeats every 2L. So if I take a function which does what my guitar string does here, and then I flip that over and repeat it over and over again to make a periodic function, if I write that function as a Fourier series, what I've done is I've written what my guitar string is doing from 0 to L as a function of harmonics on the string, right? And then once I have that, right, that the y of x is equal to some, sum from n equals 1 to infinity, a sub n sine n k naught x, right? Once I've written, these are the harmonics on my string, once I've written my function, my initial state, as a sum of these harmonics, to make this a function of time, I just have to come along and say, well, I know how these harmonics on the string oscillate, and omega 1 t, right? Or maybe call that naught. It's really the frequency and wave number of the first harmonic. All right, so you could call it omega naught or omega 1. It means the same thing to me. All right? So once I write my Fourier series allows me to write it as a sum. I just get these coefficients, these constants that go in front of my sines. Then I can write the whole shape of the string as a sum of these. And then for each term in the sum, I can just tack on how that thing evolves in time. Now it can get tricky. There can actually be a phase shift in time. But we're going to do problems where there is no phase shift. All right? So here's an example, a plucked string. I take my guitar string out, pull it out, let it go. This is what my string will do. How do I know it's going to do this? Well, because I took that triangle-shaped wave, all right? I wrote it as an inverted, stop changing slides, please. I wrote it as an inverted thing, an inverted periodic, I inverted it about the origin, mirrored it about the origin, repeated it over and over again, did a Fourier series of that, got the shape of my string, multiplied by each of the harmonics by their time dependence, and then I let it go, and this is what happens. Now, a real guitar string will do something a little wacky because they have dispersion. So each of the frequencies is actually not quite just n times the fundamental, but if we know what the frequency of each of those harmonics is, we just plug them in and let it go. Here's an example of a whack string, like a piano. A piano string, you don't pluck it, you don't pull the string out and let it go. You whack it with a hammer, so you can kind of imagine at time t equals 0, the string is flat, but some little piece of it has a velocity to it. All right? You can also I solved this. I just did a Fourier series of my initial state, multiplied each term by the time dependence, and here's what my string does. Okay, so what we did is an example of using a Fourier series or a Fourier transform of a non-periodic function. So technically what we did is a Fourier series. All right, so there's two different ways you can do a Fourier series of a non-periodic function. One way is to realize that a non-periodic function is just periodic with an infinite period, right? I snap my fingers and I have to wait forever for it to happen again. All right, so it's non-periodic, but I can think about it as being periodic with an infinite period, which means that omega naught is 2 pi over t. All right, so when I sum my sines together, right, I've got sine of n omega naught t, right? I have 1 times 0, I have 2 times 0, I have 3 times 0, I have 4 times 0, all right? But n goes all the way up to infinity. What do you get when you multiply infinity times 0? It turns out you can get anything. So what happens is, instead of having discrete frequencies in our sum, we end up with an integral over all possible frequencies. Now that is what we call a Fourier transform. So when it's a sum, we call it a Fourier series. When it's an integral, we call it a Fourier transform. But they're really the same thing, all right? Another way we can do this is we can recognize that finite data, real data only spans a finite amount of time. So if I take data in an experiment and I want to write it as a Fourier series, I can just pretend like that's part of a periodic thing, and I can still pull the frequencies out. That's what we did with the guitar string, right? As we said, we're only interested in what happens on the string, but we can pretend like that's part of some infinite periodic thing and get information out of it. All right? What happens when you're not looking? We don't know. Maybe we don't care. We can pretend like it repeats over and over again. So here's an example, kind of like the guitar string. I took, recorded a little bit of myself saying hello, and here's part of the waveform that the computer recorded. All right? You look at that, and it looks sort of periodic, right? It looks like it maybe has some sine waves in it, but it's not periodic. It doesn't go on for forever. But if I just say, well, let's just pretend like this repeats over and over again, and then write that as a Fourier series, you can do that, all right? And here is a plot of the amplitude of the different sine waves as a function of the wave number k, all right? And you can see, yes, my voice has specific sine waves in it. You can see those spikes. It has a lot of this sine wave, a little of that one, a little of that one, and a little of that one, all right? So even though I didn't record for infinitely long to see if my voice was periodic or not, I pretended like it repeated over and over again. That allowed me to write my voice as a Fourier series, and that allowed me to see what frequencies were in my voice. Okay, another cool thing you can do with Fourier series is circuit analysis. When you take an advanced electromagnetism course, you will learn that if you have circuits where you have things that are changing in time, so I send some signal into a circuit, it's really hard to just take some arbitrary wave and figure out what that's going to do in the circuit, unless you break that arbitrary wave up and think of it as a sum of sine waves, right? So what I'm going to do is I'm going to say, look, I've got this signal, I'm going to put it into my circuit. I can think of that signal as a sum of sines, right? So I just do my Fourier transform on this, right? I just do my integrals, I find my a sub n's and b sub n's. So for example, this signal right here, I look at the signal and I say, that is neither even nor odd, right? So it must have sines and cosines. I go and do the integrals. But if I'm really clever, notice if you shift your origin to the center right here, now you've got something where the function is actually odd. So if you look at that, you say, there's going to be it's an odd function which is offset. So when I do my cosines, I'm going to get my b sub 0 term, which is just the average of this, right? But then once I've taken account of that average, all that's left is odd, so that's the only cosine I'll get. Anyway, you go and you do the integrals and you get the b sub 0 term, right? And then you only get sines and you get this function right here, right? And basically, by doing a Fourier series, I was able to write that sawtooth wave as this function right here, just as a sum of sine waves. And as I add more sines in, you can see it starts to look more and more like a sawtooth wave. That's great. So I was able to write the sawtooth wave as a sum of sines and cosines. What's that good for? Well, imagine I'm driving an electrical circuit with this sawtooth wave. It's really hard to figure out what this electrical circuit will do with a sawtooth wave. But usually it's a lot easier to figure out what a circuit will do if you drive it with a sine wave. So I figure out, in general, if I put in some sine wave at some generic frequency, what will it do? Once I know that, I can take this thing up here and say, well, I'm driving it really with a bunch of sine waves, and I know what each of those sine waves do. So, for example, I can plot a spectrum, all right? So a spectrum of this function right here, I can plot the amplitude of the cosine in the blue and the sine in the red. And you see I have discrete frequencies, and I have different amplitudes at those different frequencies. Another way of drawing the spectrum of a sine wave is combining the sine and cosine, all right? So I combine them in quadrature, so I find kind of like a total amplitude. It's not going to let me write on it. Here we go. C is equal to the square root of a squared plus b squared. So at any given n, I can find an amplitude, which is sort of a combination of the sine and cosine. And then this other plot over here, using the right axis, I've plotted the phase, right? So the phase tells me how much of it is cosine and how much of it is sine. So that's another way of plotting a spectrum. Also, oftentimes, we'll plot a spectrum. Instead of plotting the amplitude, we'll plot the power. All right? Now, the power depends on properties of the string and whatnot. So it turns out if you try and put a sawtooth wave on a string, you end up with equal power. Even though the amplitude goes down, the power depends on the frequency as well, right? And so it turns out that if you try and put this wave on a string, each of those frequencies contains the same amount of power, and we sum up to infinity, it takes an infinite amount of power to put a sawtooth wave on a string. And that sort of makes sense, right? Because it takes an infinite amount of energy to stretch a string from here to here over no space, right? That discontinuity in the string involves an infinite amount of energy, all right? But for like if this were an electrical wave going through a coaxial cable, it turns out the electrical waves, the frequency doesn't, the power doesn't depend on the frequency for an electrical wave, just on the amplitude. And you get a power spectrum that looks something like this if I'm putting a sawtooth wave through an electrical cable. So the point is I'm just showing you how to plot a spectrum. It's just a way of representing your Fourier series on a plot. Now back to analyzing circuits. All right, so imagine, here's the power. Here's the power in decibel, in a decibel scale, a logarithmic scale. Sometimes we like to do that because then you can see the small stuff easier. Okay, now imagine though, I'm going to take my signal, I'm going to send it through a low-pass filter. Well, what I do is I say, well look, this is the spectrum of my signal before the low-pass filter, but the low-pass filter, when I send a sine wave through it, it makes it smaller and changes the phase. And how much smaller it makes it and how much it changes the phase depends on the frequency. Well, once I know how that happens for each frequency, I just go to each frequency in my sum and I multiply by the effect of the low-pass filter and my spectrum changes, right? So each term in my sum changes. The amplitudes get smaller, all right? The DC part doesn't get smaller, but all of the other ones get smaller, and the phase changes. So that's just, my spectrum is just showing me how the terms in my sum change, all right? And so I add them all together, and this is what you get, all right? So I have my sawtooth wave, and then I multiply each term in the sum by what happens to that term, to that sine wave when it goes to the signal, and then I add them all together, and I get the red curve. So this shows me if I put this sawtooth wave in, this is what comes out of my low-pass filter. So I can do a prediction. This is a mathematical calculation. Notice this sawtooth wave is a little different than one we had before. This one ramps down instead of up. The reason for that is after I'd made all the slides, I thought, you know, I should actually go and measure this in my lab and show that my calculation actually predicts what the circuit will do. Well, it turns out that my function generator made sawtooths backwards. So I flipped my equation around. I got this plot. And then I went and measured a signal going through a low-pass filter, like one that you will make when you take Physics 140. And this is what I got. So this is the theory, this is the experiment, all right? So using a Fourier series, I was able to analyze the circuit and predict what was going to come out of it. All right? Now, I should point out, everything other than the guitar string is show and tell. You're going to do the guitar string stuff in your homework. Everything else, I'm just kind of showing you stuff that you can look forward to doing later in life in more advanced classes when you use Fourier transforms. And I'm going to show you now some really fun applications of Fourier transforms. And in fact, if you don't have time and stop watching the video now, you have everything you need to do the homework, all right? But I hope you listen because there's some really fun things I'm going to show you can do with Fourier transforms. One cool thing you can do is you can make MP3 files, right? You all know about MP3 files. We store music in MP3 files. Why do we use MP3 files? Because they're small, they're compressed. How do you compress a file? All right, now imagine, remember that video, the picture I showed of the waveform of my voice. Every moment in time matters. I can't throw out particular times. But if we look at the spectrum of my voice, it turns out this plot has exactly as many points in it, as many data points as the original, the waveform I showed you earlier. And what you can see is there's not a lot of stuff going on at high frequencies. There's some very specific frequencies that matter for my voice. So what you can do is you can take a little snippet of sound, do a Fourier series, all right, and look at the amplitudes of these sine waves, and you look at them and you say, only a few of these really matter. I can throw the rest of them away. So now you've compressed your sound, right? You've thrown away the frequencies that don't matter. Now, if I do an inverse transform, I'm going to get all my data points back again, and I've lost my compression. So the way you do an MP3 file is you take a little snippet of sound, you transform it, right? You find your A's and B's. You find how much of the different frequencies. You find out which ones matter, and you keep those. You throw away the rest. Now your spectrum is compressed. You save that compressed spectrum. Then you grab the next little piece of sound, and you do the same thing and save that compressed spectrum. So an MP3 file is just a series of spectra of little pieces of the music. Then to play it back, your phone takes a little spectrum, does the inverse transform, plays it out your headphones. Takes the next little spectrum, does the inverse transform, plays that out your headphones. So an MP3 file is basically the Fourier transform of little bits of your music. JPEG compression. It turns out JPEG compression is a lot like MP3 compression, but in 2 dimensions. So I can think of a picture as just being a function of position of 2 coordinates. All right. Now, it turns out it's 3 functions, right? We have a red, a green, and a blue component. But if you separate them out, you can take each component and do a 2-dimensional Fourier transform, right? So this is the 2-dimensional Fourier transform. I've actually combined the components here just because it's too hard to look at them all. But really, you do them separately. You take the red, the green, and the blue components of your picture. You do a 2-dimensional Fourier transform, and you get something that looks like this, where white means a big number and black means a small number, and the kind of the position on this plot tells you what frequency it is, because you have a 2-dimensional frequency. So over here, along this line, are sine waves traveling in this direction with higher and higher frequency. Over here, you have sine waves traveling in that direction with higher and higher frequency. Along this direction are sine waves traveling in that direction, and so forth. So you go out to a particular frequency in a particular direction, and you look and you say, how bright is that spot there? That tells me how much there is of that particular sine wave. Okay? So you do that and you look at this and you say, well, look, there's a lot of really dark points. Maybe those frequencies don't matter. So maybe I'll get rid of some of those, and now I've got compression. I do the inverse transform, I get my image back, and it looks pretty much like the image I started with. So JPEG compression does a Fourier transform of the image, and then looks to see what frequencies don't matter, and throws them out. All right, if you've ever watched an MPEG movie, AVI movie, basically any video that you watch on the internet, any DVD or Blu-ray video that you watch, those are compressed. And the compression algorithms they use Fourier transforms in a similar way to JPEG and MP3 compression. The soundtracks are compressed using MP3 compression. So without Fourier transforms, Fourier series, we wouldn't have all this cool stuff. You can also do some cool digital signal processing. All right, there's a device called an auto-tuner. It's sort of cool, but it's also sort of sad. In an auto-tuner, what you do is you sing into a microphone. The signal from the microphone goes into this box. The box does a Fourier transform of your singing and looks at the frequencies in there. And it says, you know, it looks like you're trying to sing a B flat, but you're a little sharp of a B flat. So I'm going to adjust all those frequencies down and then do an inverse transform. Now you're singing a perfect B flat. All right, it's a really cool piece of technology. However, I don't think it's a coincidence that right after this device hit the market, that's when we got Britney Spears and the boy bands. All right, the frowny face here. That is a reminder. Fourier transforms and Fourier series are very powerful mathematical techniques, but it's up to you to decide whether you will use that power for good or for evil. All right, you can also do some really cool music effects, cheap quality guitar effects. I'm all for that. You can do really funky special effects with digital signal processing, and maybe I'll have time to show you some that I've done in class. All right, but all this cool stuff you can do is made possible by a slick numerical technique called the fast Fourier transform. It turns out that somebody figured out how to do the integrals involved in a Fourier series really fast numerically. And so that's why with a cheap phone you can do MP3 compression and decompression. All right? So if you are a programmer, if you like to program computers, you might look into the fast Fourier transform and maybe try your hand at writing your own fast Fourier transform computer program. Let me now show you some things that I've done with Fourier transforms in my lab. Fourier transforms come up in my research all the time. I'm just going to show you a few things, places where they show up. One device that we use in my lab is called a Fabry-Perot Etalon, and this is used to measure whether a laser beam is like a single frequency, if the laser beam's frequency is drifting, and so forth. And the basic idea is I shine my laser beam, I've got 2 mirrors, and it reflects off of the mirrors. Now, the mirrors are pretty reflective, so you would expect when the laser beam hit the first mirror, most of the light would reflect. However, the space between the 2 mirrors forms a resonator. And it turns out if the wavelength of the laser is such that you can fit an integer number of half wavelengths between the 2, you hit a resonance, just like a resonance on a guitar string. You can actually get a lot of light coming through. So what you can do is you can shine your laser here, you can put a photodiode over here, and scan the position, the distance between these 2 mirrors, and see when your laser beam comes into resonance, and that can tell you about, you know, the properties of your laser beam, what frequency it is, whether the frequency is stable, whether it's a single frequency in your laser beam. Now we did an experiment some time ago where we were doing spectroscopy on calcium. We scanned the wavelength of the laser and saw where the calcium atoms responded. That's this green and black curve right here. That's when the calcium, when it dips down, that means the calcium atoms are scattering light. Well, to measure and see how far we had scanned the laser and whatnot, we sent the light also to a couple of these Fabry-Perot Etalons, these optical resonators. All right? And you can see when we hit a resonance on the blue and the red lines, when you hit a resonance, you get a bunch of light coming through. You get a spike. The question is, how close do you have to be to that exact resonance to get light through? Why are these resonances not infinitely narrow? Turns out Fourier transforms can tell us about that. Imagine you have two mirrors and you've got light resonating in there like a guitar string. If your two mirrors are perfectly reflective, that light will just resonate there forever, right? So if you look at the electric field at some point inside your cavity, it'll look like the top plot right there. It's just oscillating forever. It's a pure sine wave. If I write that as a Fourier series and write my spectrum, I find there's only one frequency, right? There's only one frequency. It's a pure sine wave, so I get a spike. Boom, right there, pure sine wave. But what if my mirrors are not perfectly reflective? What if they let a little bit of light out each time it hits? Well, now, if I have some light in my cavity, it's going to slowly leak out. So if I measure the electric field at some point in my cavity, it's going to oscillate, but it's going to decay. So it's like a decaying sine wave. But a decaying sine wave is not a sine wave. So what is it? It must be a sum of sine waves. So if I write this decaying sine wave, right, do a Fourier transform, find what sine waves are in it, and plot the spectrum, it looks like this. All right? It's not just a single spike, it's a spread of frequencies. Now, if my mirrors are even less reflective, they're going to let the light leak out faster. So I'm going to hit the down button. We're going to see this decay faster. What happens to our spectrum? Here we go. Boom. Right? So let's go back and forward. When it decays faster, the spread in frequencies gets wider. If it decays really fast, the spread in frequencies gets really wide. So the width of that resonance, how close I have to be to get it resonating, has to do with how long light can resonate in the cavity, all right? Because light that decays very quickly, when I do a Fourier transform of that and look at what frequencies are in that light, it's a broader span of frequencies. Now, we talked earlier about uncertainty, all right? And it turns out you can prove the uncertainty relationships using Fourier transforms, all right? And basically what it comes down to is, I'm making a wave. If I want to make a wave that lasts a short amount of time, I have to add together a whole bunch of sine waves that span at least some minimum range of frequencies. All right? If I want to make a wave that exists only in a certain amount of space, I have to add together at least a minimum span of wave numbers, right? A pure sine wave exists everywhere and at all times, right? A pure spike, right? If I have a delta function, something that just exists at one point, and a wave that just pops up at one point and goes back down infinitely fast, that lasts for zero time. It has to have all possible frequencies in it. A wave that exists in only one point has an infinite spread of wave numbers in it, all right? And somewhere in between, if you have a snap my fingers, that lasts a certain amount of time, there's a minimum range of frequencies we have to add together to make a pulse that lasts a short amount of time. All right? Now, when you learn about quantum mechanics, you find out that every object is represented by a wave, and it turns out that the momentum of an object is proportional to its wave number, which means I can solve for k and plug it into here, and you get an uncertainty relationship for position and momentum. So Fourier transforms can also tell us that when we study quantum mechanics, it's impossible to know exactly where something is and exactly how fast it's moving. And the better we know one, the greater the limits are, even in theory, as to how well we can measure the other, which is a really groovy, bizarre but real thing in quantum mechanics. Okay, another thing we worried about when we did this experiment here is this line right here. This is the spectrum of the calcium, right? So as we scan our laser, the calcium has some resonances and it scatters the light. But there was something that affected that resonance, and that was the fact that the calcium atoms were bumping into each other as they were scattering the light. And you get something called collisional broadening or pressure broadening that broadens your curve. It turns out most of this curve is actually broadened due to Doppler shifts, right? We talked about Doppler shifts. The atoms in our, so we've got this laser coming and we've got atoms flying in all different directions. So some atoms are Doppler, see the laser Doppler shifted up in frequency, some down in frequency. You average them all together and you get this broader curve. But in addition to that, there's broadening because the atoms collide with each other, and we were trying to understand that. And we realized that you could understand that very well using Fourier transforms. So if I had a pure sine wave and my atom was just sitting there absorbing it, right, it would see a pure sine wave. But well, every time my atom gets bumped into it, it gets a quantum phase kick, which is equivalent to the atom seeing the phase of the light field shifting randomly. So we said, what if I have a sine wave, but randomly, with a certain average time between it, we give it a random phase shift? And I do a Fourier transform of that, you can find that, wow, that isn't a sine wave, it's a sum of a whole bunch of sine waves. So we could figure out how the sine wave got broadened because of the collisions between the particles. And this was really cool because as we were reading, the literature on collisional broadening, a lot of it was really just hard to understand and very mathematically gross. But once we figured out, oh, I can just do a Fourier transform and there's my broadening, it made our lives really easy. For a while, at various points in my career, I've worked on atomic clocks. So let me tell you about how to make an atomic clock, and then I'll show you how to use Fourier transforms to make atomic clocks better, to better understand atomic clocks. So the basic idea with an atomic clock is you need something that oscillates. To make a clock, you need something that oscillates. For a grandfather clock, the pendulum oscillates. It goes back and forth and tells time. If you have a phone, it's probably got a little quartz oscillator, and that quartz oscillates. And by counting the oscillations, you can tell time. But the problem with a pendulum or a piece of quartz is every one of them is different, right? You manufacture two grandfather clocks, they're going to tick at a different rate. You manufacture two quartz oscillators, they're going to tick at slightly different rates. And they're also temperature dependent, right? Thermal expansion changes how they tick, all right? But the idea with an atomic clock is your oscillator is an atom. And if you take an atom or an ensemble of atoms and you isolate them so that nothing's bothering them, every cesium-133 atom oscillates at the same frequency as every other cesium-133 atom, right? So you pick a particular type of atom, and if you make a clock based on that, all clocks based on that atom are going to tick at the same frequency, all right? That's the great thing, is our atoms are these ideal little oscillators, and they're all the same, all right? So what I do is I irradiate the atom with microwaves or laser light or something, and I see if the atom responds, and I tune my oscillator to keep that oscillation on resonance with the atom, to make sure the atom keeps responding to it. As long as the atom's reacting to it, I'm on resonance, and my oscillator is at the right frequency, and I can use that to tell time. All right? Well, remember the uncertainty principle. If I want to make a good atomic clock, I need to have a very narrow transition, all right? So that if I detune even a little bit from the atomic transition, my signal drops off rapidly, and I know I need to fix things, right? If I have a very broad transition, right, I can change my frequency quite a bit, and the atom still interacts. And the key to having a very narrow transition so I can make a very precise clock is to have an atomic lifetime that's very long. An atom with an excited state that doesn't decay rapidly, because the faster it decays, the broader the transition, right? So there's this Fourier transform coupling between how fast the state decays and how broad the transition is. So we typically try and find transitions in atoms that are very narrow, where the upper state lives for a long time. All right, but it turns out even if your atom has a very narrow transition, you still get broadening because your atom doesn't interact with your light or your microwaves an infinite amount of time. So imagine I have a laser beam here, and my atom is traveling through, and we're trying to drive the atomic transition with our laser beam. If the atom responds, we know we're on resonance. If the atom doesn't respond as much, we know we've drifted, and we need to tune our laser beam to keep it on resonance so that our laser beam is a good oscillator. But the point is, even if I have a very narrow atomic transition, as the atom goes through, it does not see our laser beam as a sine wave. It sees no light, no light, no light. All of a sudden it sees some light, and now it sees no light. All right, so it doesn't see a sine wave, right, with just one frequency. It sees a shuttered sine wave. It sees nothing. Oh, now I'm in the laser beam. I see oscillating. I see nothing. So my function is 0 over here and 0 over here. You take the Fourier transform of that, and you realize, oh, that's not just one sine wave. It's a group of sine waves. And the less time my atom spends in the light, the broader the spectrum, and the more the frequency can drift before I start to notice that the atom's not interacting as strongly with it, and I can tune back. All right? So if I want to have a very precise clock, I need to have a very narrow line, but that line is effectively broadened by the time that my atom spends in the beam. So if I wanted to have a really good clock, I want the atoms to spend a long time in the laser beam so that what the atom sees is light with a very narrow spread of frequencies. Now it turns out Of course, the answer to this is like make your laser beam bigger so that your atoms spend longer time in there. Make your microwave cavity bigger so your atoms spend a longer time in the waves. Turns out that's technically challenging. A guy by the name of Norman Ramsey figured out how to get around that technical challenge, all right? And he did it by thinking about something entirely different. He thought about imaging stars with a telescope. So imagine, let's go off on a tangent here. Imagine I cut with a laser a tiny, tiny little llama-shaped hole in a piece of foil, and then I shine a laser beam through it. As we will learn when we study optics, you will not just get a tiny, tiny llama-shaped shape of light on your wall. What happens is the light diffracts. As it goes through the hole, the waves spread out and it diffracts and makes what we call a diffraction pattern. It turns out the diffraction pattern of a llama looks like this. This is what you would get on the wall, all right, if you shot a laser through this little llama-shaped hole. How do I know that? Well, it turns out the diffraction pattern, the far-field diffraction pattern of an aperture is just the two-dimensional Fourier transform of the aperture. So I just did a Fourier transform and that's what I got. The double llama aperture, here's the double llama diffraction pattern right there. Once again, I just did the Fourier transform of my double llama aperture. All right? So Fourier transforms tell you the far-field diffraction pattern for an aperture. Now imagine I'm looking at a telescope, at a star with a telescope. This circle right here represents the aperture of my telescope. The star sends out light and it goes in all different directions, but I only catch the light that comes into my telescope. All right? And because of that, when I look at my detector, I don't get just this tiny, tiny spot for my star, I get a blob. I get the diffraction pattern of my telescope's aperture. All right? Now it's kind of hard to see what this blob looks like, so I'm just going to take a cut right through the middle and plot it here, and that's what it looks like. That's the intensity as a function of position. That is the diffraction pattern of a circle aperture. All right? That's the Fourier transform of a circle. Now imagine that I'm looking at a star and I see a little bump in the top of here, and I ask myself, is that just noise? Or maybe do I have two stars on top of each other and their diffraction patterns are adding together? If I want to get more resolution so I can resolve smaller things and tell if that's two stars or one star, I need a bigger telescope, right? The Fourier transform of something big gives me something small. The Fourier transform of something small tends to give me something big. So I need a telescope with a bigger aperture. Well, imagine I can't afford to build a telescope with a bigger aperture. There's a little trick called apodization. And in apodization, this is what you do. You block the middle of your telescope. You only let the light go around the edges. When you do that, you get a diffraction pattern that looks like this. And if I take a cut through it, so you can see, plot it and see what it looks like this. So the black line is what you get with the full telescope. The red is with the apodized telescope. Now, the red line's kind of small because you get less light in when you block the middle. But if I multiply it, I normalize it so these two have the same peak, now you can compare the black line with the red line. The black being the full telescope, the red being the apodized telescope. The diffraction pattern of the red of the apodized telescope has lots of bumps in it, and that can be annoying when you go to analyze your image because you get all these ghost images. But the cool thing is, the very central peak is a little bit narrower. By blocking the middle, we made it a little bit narrower. It gives us just a little bit more resolving power to tell, is that one star or two stars, all right? Well, Norman Ramsey, he's an atomic physicist, and he's thinking about apodization, and it occurs to him, the cool thing about apodization is not that that central peak gets narrower. The cool thing is that it doesn't get wider, all right? It's almost the same width as what we got with the whole telescope. So he realized the parts that mattered for making that central fringe was the light at the edges. He applied that to an atomic clock, and he said, look, if the atoms interact with my narrow laser beam or a narrow microwave cavity, I get lots of Fourier broadening. If they interact with a broad one, the atoms see the light for longer, the Fourier broadening is narrower, and I make a better clock, but that's harder to make. Well, he says, what about this? Instead of a wide pulse, how about two narrow pulses separated in space? So instead of the Fourier transform of nothing, 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 wiggle, 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 nothing, 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 now we're going to take the Fourier transform of nothing, 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 wiggle, 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 nothing, 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 wiggle, 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 nothing, nothing, nothing. And when you do that, you get a spectrum that looks like this, all right? And it turns out the envelope, kind of if you were to connect the peaks and draw kind of a smooth line over that, you get something which is about as wide as the spectrum you would get for a single interaction, a single laser beam or a single microwave cavity. When we put the two of them together, it gets modulated so that inside of that smooth thing you have these sharp peaks, and that middle peak, it's about as narrow as what we would have gotten for the peak if we'd had light all the way across here. All right, so Ramsey figured out you can make better clocks easier by having it interact with your electromagnetic radiation, with your waves, twice instead of once. This is known as Ramsey's method of separated oscillatory fields. There is an interpretive dance that goes with it, and it's beautiful. But anyway, it won Norman Ramsey the Nobel Prize in 1989. All right, I've rambled on a long time about applications of Fourier transforms, and like I say, in this class you are only going to do the guitar string. So most of what I've told you in the last 3/4 of this talk is just so that you can get excited about Fourier transforms. You'll see them over and over again. If you continue in science or engineering, you will see Fourier transforms over and over again. And if you don't, you're probably doing something wrong and missing out on some cool things that you could do with Fourier transforms.